Consider the audio you are listening to right now. Whether you have headphones on or you're just, listening through a speaker in your car, the voice you hear doesn't actually exist in the space around you.
Right, it's literally just moving air.
Exactly.
Right.
At its absolute core, this audio is just invisible, meaningless pressure waves wobbling through the air. That is all it is. But somehow your brain instantly translates those physical wobbles into English, into complex concepts, and into emotion. How on earth does a physical vibration just become an electrical thought?
Well, it is arguably one of the most astonishing translations in all of human biology. We are taking raw kinetic energy molecules, literally bumping into each other, and turning it into an instantaneous three-dimensional map of the world around us.
And that is the mission of our deep dive today. We're going to trace that exact journey, how sound becomes a signal. Okay, let's unpack this, because if you look past the dense medical vocabulary, hearing is basically an incredible relay race. The body has to collect the sound, amplify it, sort it by pitch, and finally convert it into electricity.
And what's really fascinating here is that the scientific understanding of this relay race has completely flipped over the last few decades. For over a century, the medical consensus treated the human ear as a completely passive device.
Like it was just a dish catching sound waves.
Exactly. The assumption was that the ear was basically a fleshy microphone wired to a fleshy telephone line, just sitting there taking in whatever hit it.
I think that's how most of us still picture it.
Right, but we now know that is fundamentally wrong. The ear is a highly active, energy-consuming amplifier. Under the right conditions, it actually generates its own mechanical energy. The ear physically pushes back.
Wow.
Yeah, and for everyone listening to us right now, this isn't just anatomical trivia. Understanding this delicate, hidden machinery explains why you might pass a clinical hearing test with flying colors, but still find it impossible to hear your friends across the table in a noisy restaurant.
Oh, that happens to so many people.
It does, and it definitely explains why the volume you set your headphones to today is going to dictate your brain health decades from now.
I am definitely guilty of cranking my headphones up when I'm at the gym, so I really need to hear this. Let's start with the physical hurdle. To hear anything, the body first has to funnel that wobbling air toward the eardrum, which kicks off a massive physics problem.
A profound physics problem. So the visible part of your ear, the pinna, and your ear canal gather those air pressure waves and direct them at the tympanic membrane, the eardrum. It's this incredibly delicate, taut cone, roughly 8 to 10 millimeters across, and thinner than a sheet of paper.
Okay.
But the real challenge lies deep behind that eardrum. The inner ear, where the actual conversion to nerve signals takes place, isn't filled with air. It is completely filled with fluid.
Which introduces something called the impedance mismatch. I was trying to visualize this earlier, and it's kind of like, well, imagine you're standing at the edge of a swimming pool, and your friend is underwater, completely submerged.
Right.
If you stand on the pool deck and yell at them, they're barely going to hear a thing.
Because of the drastic difference in density between the air and the water, roughly 99.9% of the sound energy just bounces right off the surface of the fluid. It's deflected and completely lost.
Wow.
Yeah, if human anatomy consisted of just a tube of air leading directly to a sac of fluid, we would be profoundly deaf to most of the natural world.
So the body has to somehow force that sound into the fluid. We have to boost the signal tremendously just to overcome the pool water effect. And the body solves this using the middle ear, specifically the three smallest bones in the human body.
The malleus, the inhus, and the stapes, or, as they are more commonly known in English, the hammer, the anvil, and the stirrup.
The scale of this machinery is just hard to wrap your head around.
To give you a sense of scale, that final bone, the stirrup or stapes, is roughly the size of a single grain of rice.
A grain of rice?
Yes. Its footplate is the smallest bone-fluid interface in the entire body. And this is where the sheer brilliance of evolutionary mechanics comes in. Your eardrum is roughly 17 to 20 times larger in surface area than the tiny footplate of that stapes bone.
Oh, I see. So it's a concentration of force. You have all this atmospheric sound pressure collected on a relatively large surface area, the eardrum being funneled down and focused entirely onto this tiny rice-sized point.
Exactly.
It's like stepping on someone's foot with a stiletto heel instead of a flat sneaker.
That is a perfect analogy. The pressure is vastly multiplied. Add in the lever action of those three tiny bones pivoting against each other, and you get a massive mechanical advantage.
So it makes up for the fluid bounce-off.
It does. By the time the sound reaches the fluid of the inner ear, the middle ear has boosted the pressure by a factor of 20 to 30 times. It completely recaptures that 99.9% energy loss.
It is an incredible piece of bioengineering. But before we follow that vibration into the fluid, we should clear up a really common misconception here. We grow up thinking the eardrum is the primary organ of hearing. Like, if you puncture it with a cotton swab, you're deaf forever.
Yeah, that's not quite right. The eardrum is entirely mechanical. It is simply a relay device, much like the skin of a snare drum. It vibrates and transfers kinetic energy. If it is damaged, it can heal, or it can be surgically repaired.
Right.
In fact, even if you were to lose your eardrum and those three little bones entirely, you wouldn't necessarily be deaf, provided your inner ear fluid and nerves were still intact.
Because sound can still vibrate straight through the solid bones of your skull to reach the inner ear. Bone conduction.
Exactly.
Which is wild to think about. You can hear through your own skeleton. But let's follow the normal path. The tiny stirrup bone is now punching this amplified sound wave into the fluid of the inner ear, specifically into this snail shell-shaped organ called the cochlea.
Right, the cochlea.
Now we have a new problem. That fluid is carrying every single frequency of the sound at the same time. The low bass notes, the high-pitched whistles, everything jumbled together. How does the ear sort that chaos out?
That specific question actually sparked one of the most intense scientific debates of the 19th century. In 1863, the brilliant German physicist Hermann von Helmholtz proposed what he called place theory.
Okay.
He suggested that inside the fluid of the cochlea, there were thousands of microscopic resonating fibers. He believed each fiber was tuned to a specific frequency, much like the strings inside a piano.
So a high-pitched note would magically find and vibrate a short, tight fiber, and a low bass note would vibrate a long, loose fiber. The physical place of the vibrating fiber would tell the brain what pitch it was hearing.
Exactly. Helmholtz relied on the physics of resonance, which made logical sense at the time. But in 1886, an English physiologist named William Rutherford completely rejected that.
Oh, really?
Yeah. He countered with frequency theory, which also became known as telephone theory. Rutherford argued that the ear doesn't have individual piano strings. He proposed that the entire membrane inside the cochlea just vibrates as a single, unified structure, perfectly matching the incoming sound wave.
Like a telephone wire carrying an alternating electrical current.
Exactly, and the auditory nerve simply fires at that exact same rate.
So if a 500 hertz tone comes in, which is 500 vibrations a second, the whole membrane vibrates 500 times a second, and the nerve fires 500 times a second. It sounds elegantly simple, but there's a biological speed limit there, isn't there? Neurons can't just fire infinitely fast.
But they cannot. Neurons have what is called a refractory period. After a neuron fires an electrical spike, it needs a tiny fraction of a millisecond to chemically reset itself before it can fire again.
Right.
Because of this necessary reset time, a single neuron simply cannot physically track frequencies above roughly 1,000 hertz on a one-to-one basis.
And human hearing goes up to something like 20,000 hertz.
Yeah.
So Rutherford's telephone theory totally breaks down for higher pitches.
It fails completely for the high notes. Modern auditory science recognizes that the body actually uses a blend of both theories.
Oh, a blend.
Yeah. For very low pitches, groups of neurons can team up and fire in volleys to match the frequency, a process called phase locking. But for the vast majority of human hearing, the ear has to rely on spatial sorting.
Here's where it gets really interesting. Because finding out exactly how that spatial sorting works required some truly bizarre science. Enter Georg von Békés.
Oh, Békés is a legendary figure in biophysics. Working mostly alone in a Budapest laboratory from the 1920s through the 1940s, he refused to just rely on mathematical theories. He wanted to see, with his own naked eyes, exactly how this microscopic sorting worked.
And his methods were, well, extreme. He didn't just use human cadaver ears. He used anatomical specimens from cattle and even elephants to get structures large enough to observe.
Yes, elephants.
He would rig these ears up, shine strobe lights into the fluid-filled cavities, and physically watch the microscopic membranes vibrate in real time under a microscope.
It was observational science at its most rigorous. What Békés saw proved that Helmholtz was half correct. Helmholtz was right that the cochlea sorts sound spatially, but he was entirely wrong about the piano strings.
So no strings.
No strings. Békés observed that the membrane inside the cochlea, the basilar membrane, is a single continuous sheet. When sound punches into the fluid, it creates a traveling wave that sweeps along this membrane.
Like snapping a wet towel.
precisely like a wave down a whip. And because the basilar membrane is stiff and narrow at the entrance and wide and floppy at the far end, the traveling wave reaches a peak height at a very specific geographical location depending on the frequency.
Okay, I think I see where this is going.
High frequencies, like a piercing whistle, peak almost immediately at the stiff entrance or the base of the cochlea. Low frequencies, like a deep bass drum, travel all the way down to the floppy tip or the apex before they peak.
So the ear literally maps out pitch geographically. Every pitch has an exact zip code inside the cochlea.
The scientific term is tonati, and this physical map of frequencies is so fundamental it is preserved all the way up through your brainstem and directly into your auditory cortex. Your brain literally contains a spatial map of pitch, all derived from where that fluid wave peaked.
That just blows my mind. Casey won the Nobel Prize in 1961 for observing that. But wait, I need to push back on this for a second. If this tonotopic map is so incredibly complex and delicate, how does a modern cochlear implant work?
That's a great question.
I know scientists in the 1970s, like Graham Clark, used this map to invent the implant. But you're telling me they just shove a man-made electronic wire into this delicate fluid sac, and it magically recreates a Beethoven symphony.
Yeah.
Shouldn't that just sound like robotic, chaotic noise?
Honestly, early on, many scientists thought it would just be useless robotic noise. The implant works by threading an electrode array directly into the cochlea, entirely bypassing the natural mechanics. It sends electrical shocks to the base for high notes and the apex for low notes.
Right.
And you're partially correct. When a patient first turns it on, it often sounds like digitized, garbled static. It does not sound like natural hearing immediately.
So how do they eventually understand speech?
Neuroplasticity. Because the spatial map is correct, highs at the base, lows at the apex, the brain takes that crude electronic input and, over months of practice, rewires itself to interpret those distinct electrical pulses as meaningful sound.
Wow, the brain just figures it out.
It does. Today, over 700,000 people have received these implants. Many can converse on a telephone despite having zero functioning natural hearing mechanics. It is a direct engineering payoff of understanding exactly where the ear sorts frequency.
Okay, so we've collected the sound from the air, amplified it with the tiny bones, and sorted it geographically along the fluid of the cochlea. But it's still just a physical wave moving through liquid. How does that physical motion become an electrical spark for the brain?
To understand the conversion, we look to the organ of Corti. Discovered in 1851 by the Italian anatomist Alfonso Corti, this is the actual sensory structure sitting right on top of that vibrating basilar membrane.
And this is where we finally meet the famous hair cells, right?
Yes. You have roughly 16,000 of them per ear, divided into a single row of inner hair cells and 3 rows of outer hair cells. And sitting on top of each cell is a tiny bundle of tubes called stereocilia, which look like microscopic hairs under an electron microscope.
16,000 sounds like a big number, but compared to the millions of photoreceptors we have in our eyes, that is an incredibly tiny workforce handling every single sound we will ever hear in our lifetime.
It is a microscopic workforce, and to be clear, they are not hair. They are not made of keratin. They are highly specialized sensory neurons. And the way they convert motion into electricity, a process called mechanotransduction, is an absolute marvel of biological speed.
This part is incredible to me. With most of our other senses, like smell or vision, a receptor detects a photon or a molecule. It triggers a complex chemical cascade, and eventually that creates an electrical signal. There is a chemical middleman taking up time.
And chemical middlemen take milliseconds to process. Hearing skips the chemical step entirely. Yes. When the basilar membrane flexes from that traveling wave, those stereocilia bend. And when they bend, they literally physically pull open ion channels at their tips.
It's like pulling open a trapdoor with a microscopic string.
That is the exact mechanism. Ions from the surrounding fluid instantly rush in through that open trapdoor, causing a sudden electrical spark, what we call depolarizing the cell, which signals the cell to immediately release a chemical payload onto the auditory nerve. Because it relies on a physical trapdoor being pulled open, this whole process happens in microseconds.
It has to be that fast to keep up with the complexities of human speech and music. But here is where we get back to that massive paradigm shift you mentioned at the very beginning of our deep dive.
Right.
For a long time, researchers assumed these hair cells just sat there, passively getting bent by the fluid wave.
Which brings us to the late 1970s and 1980s, and the breakthroughs of researchers like David Kemp and William Brownell. Brownell discovered that those outer hair cells, they aren't just passive tripwires. When stimulated by electricity, they physically change length. They stretch and contract thousands of times a second.
Wait, The ear acts like a motor. It physically dances.
It dances vigorously.
Yeah.
It is called electromotility.
Mm.
These outer hair cells act as a cochlear amplifier. When the incoming sound wave is faint, these cells pump extra mechanical energy into the wave, sharpening the tuning and boosting the sensitivity of quiet sounds by up to 60 decibels.
The ear is pumping energy into the vibration, which means, well, ears must make noise.
They absolutely do. It's called an otoacoustic emission. Because those outer hair cells are vigorously dancing and amplifying the wave, a tiny bit of that mechanical energy leaks backwards.
Okay.
It travels back through the fluid, back through the middle ear bones, and physically vibrates the eardrum like a speaker cone, sending a sound out into the world.
Your ear literally sings back. And this isn't just weird trivia. We use this mechanism globally every single day.
It is the foundation of newborn hearing screening. A doctor places a tiny probe with a microphone into a sleeping infant's ear and plays a series of soft clicks. If the baby's outer hair cells are healthy and dancing, the ear will generate a faint, high-frequency echo and otoacoustic emission that the microphone picks up.
Without the baby having to do anything.
Exactly. It requires no behavioral response from the baby. According to the CDC, this simple physical test screens out 1 to 3 out of every 1,000 newborns in the U.S. with hearing loss, allowing for early intervention. It is one of the most successful population-wide sensory screenings in medical history.
This is phenomenal. But hearing about all these microscopic trapdoors and dancing cells, it highlights how fragile this system is. It relies on tiny, non-regenerating mechanical parts vibrating at incredible speeds, which makes it incredibly vulnerable in the modern, noisy world.
Extremely vulnerable. And this is where we have to untangle a very common public misconception about loudness and pitch. People generally assume that volume and pitch are processed the same way, that a louder sound just means the entire ear is doing the same job, but harder.
But they are coded entirely differently. As we learned from Bakersy, pitch is strictly about where the wave peaks on the membrane. Location is everything.
Loudness, however, isn't about location at all. It is primarily about how many of those hair cells fire and how vigorously they fire in that specific location.
I see.
This means acoustic damage can selectively impair one aspect without destroying the other. This is why people with hearing loss do not just experience the world as quieter as if someone turned down the TV volume. They often experience sounds as distorted, muddy, or entirely missing certain frequencies.
And it also explains why we almost always lose our high-frequency hearing first as we age or after years of going to loud concerts, because high frequencies peak right at the base of the cochlea near the entrance.
Yeah.
Every single sound wave that enters the ear, whether it's a low bass note or a mid-range voice, sweeps past that base on its way down the canal. That specific physical area takes the most cumulative mechanical punishment over a lifetime.
It is the highest traffic area on the membrane, so it wears out first. Which brings us to a massive failure in how we have traditionally handled hearing health. For decades, industrial and medical policy relied almost entirely on the standard audiogram to decide if someone had hearing damage.
That's the test where you sit in a soundproof booth and raise your hand every time you hear a faint beep.
Yes, a test of pure hearing sensitivity. But starting in 2009, research by Sharon Kujawa and Charles Lieberman proved that the audiogram misses a massive part of the picture. They demonstrated that moderate noise exposure can permanently destroy the neural synapses, the delicate chemical connections between the hair cells and the auditory nerve, before the hair cells themselves die.
So what does this all mean?
It means you can have a condition dubbed hidden hearing loss or cochlear synaptopathy. You can sit in that quiet, soundproof booth, hear all the pure tones perfectly, and walk out with a normal audiogram.
But something is still wrong.
Right. Because those neural connections are frayed, the complex signal reaching your brain is degraded. You'll find it nearly impossible to understand speech in a noisy environment, like a busy restaurant or a cocktail party, because your brain isn't getting enough crisp data to separate the voices from the background clatter.
The microphone still works, but the cable connecting it to the computer is frayed. And a lot of this damage is coming from how casually we interact with sound today. Regulatory bodies like NIOS set the safe occupational noise limit at 85 decibels for an 8-hour workday.
The crucial piece of math that the public largely misunderstands is the exchange rate. Decibels are logarithmic. They are not a linear scale like a ruler. IOH uses a 3 decibel exchange rate.
Okay.
Because a 3 decibel increase represents a literal doubling of sound energy hitting your ear, your safe exposure time is instantly cut in half.
Okay, let's do that math out loud because it's terrifying. 85 decibels is safe for 8 hours. 88 decibels is twice the energy, so it's only safe for 4 hours. 91 decibels is 2 hours.
Right.
A lot of rock concerts or cranking your earbuds to maximum volume easily hit 100 to 110 decibels. At 100 decibels, you exceed your entire day's safe limit in about 15 minutes. At 110 decibels, it's a matter of minutes, if not seconds.
The public tends to assume that listening to their favorite loud music cannot possibly be as hazardous as working an 8-hour shift in a steel mill. But the physics of the inner ear doesn't care if the kinetic energy is coming from a factory saw or a beautiful guitar solo. Mechanical energy is mechanical energy. It bends and breaks the stereocilia all the same.
And here is the harshest truth of all. Unlike a cut on your skin or a broken bone, human hair cells do not regrow. Once they're destroyed by excessive noise or natural aging or certain toxic chemotherapy drugs, they're gone forever. We have zero biological mechanism to replace them.
Which is why prevention, turning down the volume and wearing ear protection, is currently our only real safeguard. If we connect this to the bigger picture, we have to recognize that peripheral hearing, what happens inside the ear, is just the beginning of the journey.
Right.
The auditory nerve carries these converted signals into the brainstem, up through various relay stations that help us localize where a sound is coming from, and finally into the primary auditory cortex.
It is deeply integrated into how our entire brain functions day to day.
Deeply integrated. The World Health Organization estimates roughly 1.5 billion people globally have some degree of hearing loss. And large epidemiological studies have recently recognized that age-related hearing decline is one of the largest modifiable risk factors for dementia.
Because of the cognitive load. If the ear is sending a garbled, degraded signal to the brain because of those frayed synapses, the brain has to work in absolute overdrive just to decode the words. It uses up processing power, stealing resources from memory formulation and higher thinking. Not to mention, if you find it exhausting to hear people in a restaurant, you stop going. You withdraw. And social isolation is terrible for long-term brain health. Hearing is literally a public brain health issue.
It absolutely is. We've seen incredible translational successes, cochlear implants bypassing the mechanical damage, otoacoustic emissions, screening our newborns and giving them a head start. But managing our acoustic environment and protecting the delicate structures we currently possess remains paramount for long-term cognitive health.
It really makes you appreciate those invisible, wobbling pressure waves and the microscopic, lightning-fast machinery inside our heads that is translating my voice for you right now. Thank you all for taking this journey with us.
Thank you.
But before we go, I want to leave you with one final thought to mull over. We mentioned that human hair cells do not regenerate, but you know what does? Birds and fish. They can naturally regenerate these delicate sensory hair cells just days after they are completely destroyed by noise. If human hearing loss is currently permanent, what if the true future of audiology isn't just about building better mechanical implants to bypass the damage, but figuring out the biological switch to let our own inner ears heal themselves?